Forward first. Okay, so recording now. So yes, today we've got Thiel from Dresden, who's going to talk to us about the generator rank of C-star algebras.
Yeah, thank you very much for the invitation. So right, the generator rank of C-star algebras. Let's get to it right away. This talk is about generators and the generator problem. And I will start by presenting to you the generator problem for Neumann algebras. And then after that, we're looking at C-star algebras. So the generator problem for Neumann algebras, that was first formulated as an open problem by Cadison in 1967. And he, at that year at the conference, he gave a list of the 20 most prominent open problems on Neumann algebras at the time. The generator problem is number 14 on that list. And it's here. So the question is the following. If you have a von Neumann algebra M, which is representable on a separable Hilbert space, then the question is it singly generated? And singly generated just means, is there one single operator X that generates M as a von Neumann algebra? So you could say, is M the bicommutant of X and X star? And so this problem number 14 is still open. And it's actually one of the two remaining problems from Cadison's list of 20 problems. So all the other 18 ones have been solved. The other one that's still open is, of course, the famous three factor problem. So the question if the three factors are isomorphic or not. And we will see in a moment that they are actually connected, the two. So there has been a lot of research on this problem, in the sense that for more and more classes of von Neumann algebras, it has been shown that they are indeed singly generated. So I'm listing here just a few. So starting with von Neumann, I mean, he did the abelian case. Pearcey settled the type 1 case, and then Vaughan the properly infinite case. And if you take here the type 1 and properly infinite case together, this reduces the whole problem to the 2-1 case, because we know von Neumann algebras, they decompose as direct sums of types. And then this was further reduced by Willich, essentially using disintegration techniques to the factor case. So what was proven is precisely that there will be a positive solution to the generator problem for all separately acting von Neumann algebras, in the sense that they're all singly generated, if and only if that holds for every separately acting 2-1 factor. Yeah. So at that moment, it was clear that the whole problem is about 2-1 factors. And then there was further research showing that certain classes of 2-1 factors are singly generated. And the main open problem that is still unknown to this day are these free group factors. Of the free group Fk here, let's say on K generators, we don't know if these are singly generated if K is at least 3. Because if K is 2, you can actually see that it is singly generated. And you see that as follows. F2 has 2 canonical generators as a group, and these give you 2 unitaries in the factor that generate the factor. And then you take the logarithm of the first unitary and of the second one. This gives you 2 self-adjoint elements, and you take A plus IB of if A and B are the self-adjoint elements, and this gives you a generator for K equals to 2. And then for K equals 3 and more, it is not clear if you will be able to find a single generator. And if you show that these factors here are not singly generated for K at least 3, that would of course settle the free group factor problem, because then they would be pairwise not isomorphic. What is of course a possibility is that you show that they are all singly generated, and then it still remains an open problem whether they are isomorphic or not. So there is a dependence of these two problems in one direction at least. Okay, so that is the generator problem for von Neumann algebras. Let's look at the generator problem for C-star algebras next. And here the situation is a little bit more complicated because we can simply not expect that all separable C-star algebras are singly generated. Instead, we have to look at the minimal number of generators, and this is formalized by this invariant here, GEN of A. And if A is a C-star algebra, we want this number to be the minimal number of self-adjoint generators. So we want to restrict attention here to self-adjoint elements. The difference is not very big. It's a slightly finer invariant if you count self-adjoint generators than if you count non-self-adjoint generators. And that's why we want to do that. So here in the first line, I just repeated what the definition means. Yeah. So this invariant is at most n precisely if the C-star algebra is the C-star algebra generated by A1 up to AN, which are self-adjoint. And now notice, I said this on the last slide already, that if you have two self-adjoint elements, A and B, you can combine them into one generator, namely forming A plus IB. And one sees that A and B together generate the same C-star algebra as A plus IB. And therefore, A is singly generated if and only if this invariant is at most 2. So I hope that this is not too confusing. So singly generated always refers to a not necessarily self-adjoint generator. And let's see an example or a first proposition, which is standard. Namely, how many generators do you need to generate commutative C-star algebras? So let's say X is compact and metrizable. And then the result is that C of X can be generated by n self-adjoint elements, precisely if X can be embedded into R to the n. And let's look at the proof. It's not complicated. So first, if you can embed X into R to the n, you can also embed it in R to the n without 0. You just, take the embedding and shift it somewhere away from 0. And so let's call this map iota. And then you see that C of X is generated by these maps here, pi j composed with iota, where pi j are the coordinate projections from Rn to R, and there are n of them. And these functions here from X to R, we think of them as self-adjoint elements in C of X. And since this was an embedding, you can check, that's essentially the Storm-Weierstrass theorem, that these functions generate C of X. And the converse is the same idea. So if C of X is generated by n functions from X to R, we put them together and just define a map from X to Rn, sending an element or point X to this tuple, and you will see that this is injective. Because if it was not injective, meaning that for 2 points X and Y, these values are always the same, then the C-star algebra generated by F1 to Fn would not separate the points X and Y. And so would not be all of C of X. Okay. So that was warm up. So what is the generator problem for C-star algebras? It is to determine this number, to determine this invariant. And of course, that's a tough problem in general. So maybe more specifically, we are interested in knowing which C-star algebras are singly generated. And now we want to get a feeling for when this happens. So we saw in the commutative case, this happens sometimes and sometimes not. Here are two simple facts. The first one is quite obvious. If I is an ideal in a C-star algebra A, then the number of generators that you need to generate the quotient is at most the number that you need to generate A. And you simply see that by taking the elements A1 up to AN that generate A and just push them into the quotient. So that is easy to see. The second, slightly more interesting here, is a formula estimating the number of generators you need for a matrix algebra. And we see here, so the n by n matrices over A, they need roughly divided by n squared many generators that we needed for A, modulo these correction terms, and this this notation here with these brackets up. This means that I round up, right? Because gen A minus 1 over n squared, that doesn't have to be a natural number, of course, and I'm just rounding up to the next natural number. In particular, what you see here is that if A is generated by at most n squared plus 1 self-adjoint elements, then the n by n matrix algebra over A is generated by 2 self-adjoints, so it is singly generated. And an example here is, for instance, the full group C-star algebra of F2, which we see now is not singly generated because it has a quotient coming from the abelianization of F2, which is z squared, which we know with the Fourier transform is isomorphic to continuous functions on the two torus. And the two torus does not embed into R2. Yeah? So continuous functions on the two torus, that's not generated by two self-adjoints, so neither is that algebra here. But if I take the 2 by 2 matrices over it, it is indeed singly generated because this algebra, it's easy to see that we need at most 4 self-adjoints because this algebra is generated by 2 unitaries, which we can break up into 4 self-adjoints. Okay, so kind of what we see here is that if we take matrix algebras, the numbers of generators that we need goes down, and some other slogan is, the more non-commutative you are, the fewer generators you need. And you expect then that if you are very non-commutative, you need very few generators, and meaning that if you're very non-commutative, you should be singly generated. And what does very non-commutative mean? So one way of formalizing this is to say there are no finite dimensional representations. And so the concrete question here is if every separable C-star algebra without finite dimensional representations, if that is singly generated. And that's certainly a difficult question to answer. A more concrete, more focused question would be if all separable simple C-star algebras are singly generated. And the second question is less general than the first one, because a simple C-star algebra, it's either finite dimensional, then it's a matrix algebra, then you can see very easily that it's singly generated, or otherwise it's an infinite dimensional simple C-star algebra, and then it cannot have finite dimensional representations. So if you can answer the first question, you can answer the second question, but we will see that already the second question is extremely hard. So there has been some research on these questions that I want to mention here. So for several classes of C-star algebras, it has been verified that they are indeed singly generated. Separability is always a necessary condition, of course, to be finitely generated even. And for the separable properly infinite C-star algebras, it was shown by Kirchberg, unpublished, of course, that they are singly generated. And for the separable UHF stable algebras, this was shown by Olsen and Same in the 70s. And then generalizing to Z-stable algebras, this is what I did together with Wilhelm Winter. And I don't expect you to know what Z-stable means. We will come back to this later at the end. And I will tell you a little bit about Z-stable algebras there. So the main open problem is similar to the von Neumann algebra case coming from free groups, and it is if the reduced free group C-star algebras, so these are the C-star algebra analogs of the free group factors, if these are singly generated now even for k equal more than or equal to 2. Yeah, I mean, there's a difference here between the von Neumann algebra case and the C-star algebra case. For von Neumann algebras, we know at least that for k equals 2, the free group factor is indeed singly generated. For C-star algebras, we don't even know that case. The problem is what we were doing in von Neumann algebras is we were taking a logarithm of a unitary to get a self-adjoint, and we cannot do this in C-star algebras. So it's extremely difficult to determine if these algebras are singly generated, because if you could show that, you would also solve the problem for von Neumann algebras, because C-star algebra is generated by one element, and the von Neumann algebra is also generated by one element, namely the same element. And maybe here I should also point out, I mean, I am talking about, of course, for von Neumann algebras being generated as a von Neumann algebra, while for C-star algebras, I'm talking about being generated as a C-star algebra. Okay, so everybody has their camera off, so I'm not sure if I'm disconnected from the internet or not. I hope not.
I can still hear you. I think everyone's still good.
Good, cool. Yeah, it would be cool if one of you at least could turn the video on, so at least know that I'm still connected, because I have seen some other talks where this happened to speakers, that they were just cut off at some point. And okay, great, thank you. So what is the problem with the generator problem for C-star algebras? The difficulty here is that this invariant that we are trying to compute, it doesn't have the permanence properties that we would like it to have, and the permanence properties that one usually has when one works with C-star algebras. So the first example here is where something goes wrong when you pass to an ideal. And the example is very, very easy. So A, let's say, it's just continuous functions on the closed interval. And the ideal is continuous functions on the open interval vanishing at 0 and at 1. And you can see that A is generated by one self-adjoint element. But you can also see that I is not generated by one self-adjoint element, because if you take any self-adjoint in I mean, it has to go to 0 at 0 and also to 0 at 1. So you will see that whatever function it is, it will not be able to separate all the points of the open interval. And therefore, you need at least two self-adjoints to generate this algebra. And indeed, then you can do it. Here, the number of generators goes up when passing to an ideal. So that can happen. And the second example, which is illustrating a problem, is that, this invariant here can increase when passing to an inductive limit. And the example here is, again, a commutative one. It's a topologist's sine curve. So I have some pictures here. So X is that topologist sine curve in R2. It's just, I mean, the sine curve, but I close it off. So I make it a closed or a compact subset of R2. And it has the property that I can write it as an inverse limit of spaces xk that are each homeomorphic to the closed interval 0, 1. And this works like this. I mean, I just follow this sine 1 over x curve to a point, and then I somehow stop there, and I do this here. I mean, x1 is maybe like this, x2 is like this, and then go a little bit further, and so on. And you can imagine that you have maps from x to each of the x k's, and that this together gives you an inverse system, and x is the inverse limit of them. And then if you go to commutative C-star algebras, it means C of x is an inductive limit of C of xk. And now, each xk is homeomorphic to an interval. So to generate it, I need one self-adjoint. But x, it's not difficult to agree, I guess, that this space x cannot be embedded into the real line. So by what we saw before, it means you need at least two, or exactly two, self-adjoints to generate this C of x. And what happens here is that when you pass through the limit, the number goes up by 1. And if you elaborate a little bit on this example, you can also come up with an inductive system of singly generated C-star algebras. So each building block in the inductive system is singly generated, but the limit C-star algebra is not singly generated. That can happen. And this is a problem because many C-star algebras that we are interested in are given to us or have a structure of an inductive limit with simpler building blocks. And it's a standard technique in C-star algebra theory to prove something for building blocks and then push it to inductive limits. And this just doesn't work here. And this is a problem. And to deal with this, I introduced the generator rank. And the idea here is somehow to, instead of looking at generating elements, or let's call them already generating tuples, we consider stable generating tuples. And a piece of notation that will be useful is this one here. So GN, this will be the generating self-adjoint n tuples. So tuples of n elements, A1 up to AN. Each of the A1 up to AN is self-adjoint, and they together generate the C-star algebra. So A is a C-star algebra generated by them. Okay, and now the generator rank is defined simply as follows. If A is unital, then we say the generator rank GR of A is the minimal natural number, and it's possible to be 0, such that the self-adjoint n plus 1 tuples that generate A are dense in all the n plus 1 tuples. And if this never happens for any n, then we, as usual, say the generator rank is infinity. And if A is non-unital, we just use the minimal unitization. So this A tilde here is just A with the unit adjoined. And we use that to define the generator rank. And what you notice here is there's some index shift happening. I mean, here was an n, and here we have an n plus 1. I'll explain on the next slide why this index shift is a good idea. Before that, maybe just an example. So this generator rank, because of the index shift, can be 0. And it is, for instance, for the complex numbers, because the generating self-adjoint 1 tuples in the complex numbers, that's just R without 0, because you see every non-zero number is of course a generator for the complex numbers, and that is dense in the self-adjoint 1 tuples, which is just R. Okay, so why this index shift? The reason is that this is the usual convention in dimension theory, in classical and non-commutative dimension theory. And yeah, to illustrate this, I have here the definitions of some important dimension theories, starting with the covering dimension, which is the usual dimension of topological spaces. And the dimension of a space X is at most n by definition, or maybe that's here is rather equivalent reformulation. If for every finite open cover, you find a finite open refinement V that can be colored with n+1 colors. So here's the index shift. And n+1 colors means that I can break off this refinement into disjoint subsets V0 to Vn, and I give the sets in V0 the color 0 and so on. And it means that I want to require that the elements in Vk are pairwise disjoint. So that's the classical covering dimension, something which is very important in C-star algebra theory is the nuclear dimension. It doesn't play any role later on in the talk, but if you've seen it, or maybe not, here is a reminder of the definition. The nuclear dimension of A is at most n if the identity map on A can be approximated or approximately factored by completely positive maps through a finite dimensional C-star algebra with the property that the map phi is the sum of n+1 orthogonality preserving maps. And again here, n+1 and n. And then the last one is the real rank, another important dimension theory for C-star algebras. And it is defined as follows. The real rank of the unitary case of a unitary C-star algebra A is at most n if the n+1 tuples that generate A as a left ideal. So this means that the sum of AK square is invertible, that this is dense in here. And you see that the real rank is very similar in spirit to the generator rank. Yeah, so some tuples are dense in all tuples. And you can actually show that the real rank is a lower bound for the generator rank. And yeah, so this is something one can prove. And to have a formula like this, one needs, of course, to use the same index shift. Yeah? Otherwise, you would have to put a +1 here somewhere. Now, let's compare the two invariants that we saw so far. So here on the top is just a reminder of what this meant. These are the generating self-adjoint n-tuples. This invariant here, gen A, was at most n by definition if this set is non-empty, right? Because if I can generate A by n self-adjoint elements, I will find exactly just an element here, and so this set is non-empty. The generator rank, however, is not about non-emptiness of the set, but about denseness. Okay, modulo the index shift with the n+1 here. So we see right away that this number here is always dominated by the generator rank +1. But let's look at the lowest values. So I mentioned before, this number at most 2 means exactly A is singly generated, generated by 2 self-adjoints, while generator rank at most 1, you can show that this means the following. It means that the non-self-adjoint generators, the x's in A, such that A is generated by X, is a dense and automatically G delta subset of A. So denseness is what you get from generator rank being at most 1, and a dense G delta subset, that's what one sometimes calls a generic set. So the idea, I guess, is that if you randomly chose, or you close your eyes and you pick one element from A with chance 1, so almost always it will be automatically a generator. This is what generator rank at most one means. And now the next example shows that these two invariants can be very different from each other. So the minimal number of generators can be much smaller than what the generator rank records. And the example that shows this is of this form, a commutative C-star algebra, tensor matrix algebra. So here, for simplicity, let's take the k-dimensional cube, tensor it with the d by d matrices. You can compute exactly how many generators you need. It's exactly this formula that we saw before, dimension of the space -1 over d squared plus 1. The generator rank you can also compute. We will see this a little bit later. I just wanted to make this point here already, that you see something is happening here. The left formula is going down with d squared, so much faster than the right formula here, right? The right formula goes only down linearly in d, roughly, and the second one is quadratically in d. And using this, you can, I mean, if you put a lot of these examples, so to speak, together, so a cube that is d square dimensional and the d by d matrices over that, the left formula will always give you at most 2. So we get that if you sum all these things up, that algebra will be singly generated by 2 self-adjoints. But the generator rank gets bigger and bigger. It's actually infinite. So this is maybe the extreme case that can happen. So now comes maybe the main theorem, the main reason for introducing this notion at all is the permanence properties of the generator rank. And they are now very nice. And that's the main difference. So somehow you pay the price that the generator rank is maybe just an upper bound or maybe a bad upper bound for the number that you actually want to compute, I mean the minimum number of generators. But what you gain from this is that it has very nice permanence properties. In particular, it does not increase when you pass to ideals, which is not easy to see. It doesn't increase when you pass to quotients. This is relatively straightforward. And you also even have an estimate for the generator rank of A in terms of an ideal and a quotient. And secondly, and this is most important, if you have an inductive limit, then you have this formula, estimating the generator rank of the inductive limit in terms of the generator ranks of the C-star algebras that are in the inductive system. And with this second part here, which is proved with some kind of Cauchy sequence argument, you get right away a corollary, namely that you can handle AF algebras. So AF approximately finite dimensional ones, by definition, just inductive limits of finite dimensional C-star algebras. If you have such an algebra A, you get right away that it has generator rank at most 1. So in fact, a generic element is a generator. And in particular, and this was not known, all AF algebras are singly generated. So this new invariant actually is allowing you to sometimes solve the generator problem for certain classes. And the proof, modulo the theorem, is not difficult. What you have to show is that every finite dimensional C-star algebra has generator rank 1. Finite dimensional ones are just direct sums of matrix algebras. So essentially we have to show this here. Generator rank of a matrix algebra is 1. And this means that 2 self-adjoint matrices should be approximated by matrices that generate the matrix algebra. So we start with A and B. We conjugate by some unitary to ensure that A is diagonal. And conjugating with the unitary, that yeah, that's a isometric operation, and it also doesn't change the question whether two things generate a C-star algebra or not. So I may as well assume from now that A is diagonal. And then what I do is I approximate A by a diagonal matrix with pairwise different non-zero eigenvalues. So the entrance on the diagonal should just be non-zero and pairwise different. And the matrix B, I just make sure that all the entries are non-zero. And I can surely do that. And now, why do these two perturbed matrices generate the matrix algebra? Because from A, or from the perturbed A, I get the diagonal matrix units. And then together with B, which has every off-diagonal entry non-zero, I get also the off-diagonal matrix units. So the whole matrix algebra. Okay, so this is the outline of at least the one crucial step here to proving that AF algebras all have generator rank 1. Okay, now next let's look at the commutative case, and let's look at compact metrizable spaces and the generator rank of C of x. And there's a nice formula for this, and it says that this is just the dimension of x times x, Cartesian product of x itself. And let's see a sketch of this proof as well. So we identify these self-adjoint n+1 tuples in C of x just with functions from x to r to the n+1. And now essentially it really is the Stone-Weierstrass theorem, which tells us that such a function generates C of x precisely if the function is non-zero everywhere. The condition A, f of x is non-zero. And condition B, it separates the points. So f of x should be different from f of y if x is different from y. And so this means that the generator rank of C of x is at most n, if and only if these two conditions here are satisfied, A and B. The first one is I should be able to approximate every function from x to r n+1 by one that misses the d0. Yeah. So that takes care of A. Yeah? So I want the functions that are continuous and non-zero everywhere. I want them to be dense in all the functions. And the second condition is I want the functions that are injective. So E here means embedding. So the embeddings of x in Rn+1 without 0, that should be dense in all the continuous functions from x to Rn+1 without 0. And these two questions have been studied in point set topology, and they are connected to dimension theory, of course. So it is a classical result that A, the first condition here, happens precisely if the dimension of x is at most n. So that's a classical result. You will find this in every book on dimension theory of topological spaces. The second condition is not so standard. Or the answer, it says that this happens precisely if the dimension of x cos x is at most n. And so this is proved, or it can be derived, let's say, from results in cohomological dimension theory, and more specifically, maybe what is called unstable intersection theory. So this is something which has been developed by these people, Jarnishnikov, Levin, Repov, Shepin, and West, and others. So there's a whole school of people doing these things. And now the theorem follows from the observation that the dimension of x is always bounded by the dimension of x cross x, meaning in some sense that if condition B is satisfied, then condition condition A is also automatically satisfied. So the more restrictive condition is B, and that determines the generator rank of C of X, and it's then dimension of X cross X. Okay, so here on top, I just repeated the theorem again. And let's see an example to maybe illustrate what is going on. And the example is again the interval. So it is easy to see, I said this before, now I write it down even, that this algebra is generated by one self-adjoint. Namely, you just take the function sending x to 1 plus x. Yeah. Just make sure that the function is not 0 anywhere and it separates the points. Okay, but what does the generator rank of this algebra? What is it? It is the dimension of the interval times the interval. And of course, that's 2. Meaning that because of the index shift, the generating elements in here, so they are only dense for n equals to 3. So neither the 1 tuples nor the 2 tuples that generate C of the interval are dense. I have to really go to the 3 tuples. And yeah, for n equals 1, it's easy to see that this isn't sufficient because, I mean, you take this function here that maps x to -1 to 2x. So this just goes through 0, and you cannot approximate this function by functions that are invertible, because you will always have the value 0, will always hit 0, because we're looking at real valued functions. And n equals 2 is also not sufficient. And yeah, what this means is that there exists a map from the interval to R2, which cannot be approximated by embeddings. Maybe that maybe it's not so obvious, but it's actually also not so difficult to see maybe what it is. One possibility is just a curve that is self-intersecting. I mean, just take something like this, like something that intersects somewhere, and then you can see, but it's not immediate to prove, but topologists do this for us, that if you perturb curve a little bit, there will still be some intersecting points somewhere. So you cannot approximate it by embeddings, and that's why 2 tuples are also not good. You have to go to 3 tuples. And maybe if you wondered why I write dimension of x times x and not 2 times dimension of x, the reason is that there is a subtlety here. The dimension of x times x is usually just 2 times the dimension of x, but sometimes it is that -1. Yeah, the spaces that we know, they always have this property that it's just the first one here. So that's the standard case. Now this happens for CW complexes, happens for manifolds and so on. And you actually have to work quite hard to construct a space where the dimension drops down by 1 if you go to the Cartesian product with itself. But such spaces exist, and they were constructed by Bolchanski in 49. Okay. Now, in C-star algebra theory, there's kind of a hierarchy of complexity, maybe with the commutative C-star algebras as the maybe easiest ones. And then what comes next are maybe homogeneous C-star algebras, and then in the next step, subhomogeneous. And on this slide here, I just consider these two things already at the same time. So we would say that a C-star algebra is D subhomogeneous if every irreducible representation of A has dimension either exactly D or at most D. So the typical example here is for D homogeneous, it's the the d by d matrices over a commutative C-star algebra. C of x tensor MD. You can see that every representation of this algebra is exactly d-dimensional, and we call it d-homogeneous. And subalgebras of this algebra, they will be d-subhomogeneous. And there are very nice structure theorems for these classes of algebras. So this is very classical. The first one for the homogeneous case says that essentially the typical example here, this is really how locally all the homogeneous algebras look like. So let's say unital D-homogeneous, then we first know that the primitive ideal space is compact and Hausdorff. And we also know that A is the section algebra of a locally trivial bundle over the primitive ideal space with each fiber isomorphic to the D by D matrix algebra. So this here, you can think of it as the section algebra of a trivial bundle. And so what can happen in general is that, so I cannot just write it down like this, but it will be locally looking like this. And now there's a structure theorem for the subhomogeneous case as well. A subhomogeneous algebra, I always get from it canonical chain of ideals, as written here, such that the successive quotients are homogeneous. And so these ideals, they really correspond somehow to the part or the elements of A where all the irreducible representations have dimension at least k. So you can think of subhomogeneous algebras as somewhat iterated extensions by homogeneous algebras. And I mean, using these two classical results, I was able to compute the generator rank of all subhomogeneous algebras. And this works as follows. So if you have, unital is actually not really needed, but separable, say D subhomogeneous C-star algebra, I need to look at the parts of the primitive ideal space that correspond to irreducible representations of a certain fixed dimension. So for each k at most d, I will call that xk. And xk is this part of the primitive ideal space. You can show that xk is a nice Hausdorff space, locally compact. And now the generator rank can be computed from the dimensions of these spaces. And here, what occurs here is dimension of x1 times x1, and that corresponds the same formula that we had for the commutative case. And the reason is, of course, that x1 is really is the part of the C-star algebra. It corresponds to the abelianization. It corresponds to the largest commutative quotient of A, and that is the generator rank of that. And then you have all the other homogeneous parts, and there is this formula. The dimension of that part plus 1, and then divided by the size of the irreducible representations. And what you notice here is the following. If you take a subhomogeneous algebra where the generator rank is finite, so this expression here is finite, and you tensor with a sufficiently large matrix algebra, then this number goes down to 1. And the reason is that when I tensor with an n, what is happening is that these xk's, they get shifted by n. But if I shift them by n, what is happening is the first part here disappears, and then here I just divide by higher and higher numbers. And so, I mean, if n is large enough, this will be 1. The generator rank of A tensor Mn is going down to 1. And if A is subhomogeneous, but we don't know that the generator rank is finite, then we can use a little trick. We can actually always write A as an inductive limit of subalgebras that have finite generator rank. And if we put these two things together, what it tells us is what is written down here. For any subhomogeneous algebra, if I tensor it with the UHF algebra, it has generator rank 1. And so just a reminder, what is a UHF algebra? It is an infinite tensor product of matrix algebras of the same size here. So MP infinity is this tensor product of countably many copies of MP. And yeah, I mean, I get this formula down here. What I use, of course, is that the generator rank behaves well with respect to inductive limits. I take the A, I first approximate it by subhomogeneous algebras with this property here. Then I use the first thing here, that if I take a sufficiently large matrix algebra, I have dimension 1, and then I pass to the limit again. I get this here. Okay, and that's good to know. In the next step, we want to go from UHF algebras to a more general class. And somehow this next step here now is the in the hierarchy that I mentioned before, that maybe starts with commutative, then homogeneous, then subhomogeneous algebras. The next thing is approximately subhomogeneous algebras. And we call a C-star algebra A approximately subhomogeneous if it is an inductive limit of subhomogeneous C-star algebras. And yeah, this class is very interesting because it includes many interesting examples and other constructions of C-star algebras. So I mentioned here the AF algebras that we saw before, the irrational rotation algebras, which are very famous examples of C-star algebras, certain other cross products, and so on, generalizations of these constructions. So yeah, very often you will be able to write your algebra as an inductive limit of subhomogeneous ones. And now we come to this famous Jiangsu algebra Z that I mentioned at the beginning. So what is that? I'm not going to define it exactly. It's a little bit complicated to define, but this Jiangsu algebra, you should maybe think of it as an interpolation between these UHF algebras for all the primes. So if P is a prime, for instance 2, I have M to infinity, the infinite tensor product of 2 by 2 matrices. For P equals 3, I have M3 infinity, infinite tensor product of 3 by 3 matrices, and so on. And somehow if I want to interpolate between all of them, what I get is Z, and that's a simple C-star algebra that is very interesting. And we say a C-star algebra A is Z stable by definition if it tensorially absorbs the algebra A. Yeah, so A is isomorphic to Z tensor A. And if you're coming from von Neumann algebra theory, that is really the C-star analog of being a McDuff von Neumann algebra. And now the corollary is that a separable Z-stable ASH algebra always has generator rank 1, meaning that a generic element in such an algebra is a generator. And this follows, I mean, on the previous slide, I essentially showed you subhomogeneous tensor UHF. The approximate here, that really doesn't do anything for the generator rank because we have the nice permanence properties. Where you have to work a little bit is to replace the UHF algebra by the Jiangsu algebra. But you can do that because you kind of, you interpolate between the UHF algebras. So you get this result here, separable Z-stable ASH algebras. They all have generator rank 1, and they're all singly generated. And even better, almost every element is a generator right away. And on the last slide, I want to connect this with results in classification theory. so we say a C-star algebra is classifiable, simple nuclear C-star algebra is classifiable if it's unital, separable, z-stable, and satisfy this mysterious universal coefficient theorem. I'm not gonna explain what exactly this means. Just want to mention that by the breakthrough in the LU classification program, we know that the class of simple nuclear classifiable C-star algebras is classified by their Elliott invariant, which is built from K-theory and tracial data. And that's a very remarkable result. And so these classifiable algebras, one could say they are now very well understood. And the next theorem maybe is an example of that, because it says that all these simple nuclear classifiable C-star algebras, we can solve the generator problem for them in a very strong way, in a very strong sense, by showing that they all have generator rank 1. Yeah, meaning a generic element is a generator. And the proof, the sketch here is we know that these classifiable algebras come in 2 flavors, stably finite or purely infinite. Purely infinite means that they are a Kirchberg algebra. And what is important here is that they have real rank 0. And this one can handle with different methods that I didn't talk about here today. And in the stably finite case, one knows that they're automatically ASH algebras. And that is handled then by the result in the previous slide. So all the classifiable algebras have generator rank 1. And I wanted to mention a last thing here is that Willardson constructed very interesting examples with very pathological behavior. So simple separable unital nuclear C-star algebras, which even are ASH algebras, but who have generator rank infinity. Of course, he didn't prove that. He proved that they have real rank infinity, but the real rank is a lower bound for the generator rank. Meaning that for these examples of Willardson, what we know is that the generators are not a dense set. I mean, not even the generating 3 tuples are dense in the 3 tuples and so on. What we don't know is whether these algebras are singly generated. So the difficulty is, I mean, we know that you cannot just find a generator by essentially picking one at random, picking an element at random. But of course, that doesn't mean that there couldn't be one specific generator somewhere that one has to kind of search for, but it could indicate why it is probably difficult to solve the generator problem just for these examples. And I think we don't know at the moment if the Willardson examples are singly generated or not. And it's the last I want to say. So thank you very much.
Yeah, great talk. So any questions? Feel free to unmute yourself or ask in the chat.
Just turn it on top of you. A question. I don't know. What about graph C-star algebras? What could one say about the number of generators there?
So at least the simple graph algebras, they are either AF, I think, or purely infinite, as far if I'm correct.
Could you? I didn't hear you start of your answer.
Oh, sorry. Simple graph algebras, I think, are either AF algebras or purely infinite Kirchberg algebras. Mm-hmm. So we know that these both cases are settled. I mean, AF algebras I showed you, and Kirchberg algebras I guess I also showed you. Okay. That works. So they always have generator rank 1. They are not. The generators even form a dense subset. The non-simple graph algebras, that I don't know, this might be a little bit more difficult. But my suspicion would be that they're all also singly generated. Yeah. Because they're singly generated. Yeah. I guess if it's a countable, I mean, a countable graph. Or, yeah, then some obvious restrictions that you have to put. But.
Okay, thank you. Yep.
I mean, I just had a quick question. Can you just go back to the second last slide? Yeah. So you like it was no, sorry, the next one. I meant
Oh.
the last that was not the yeah. So just with the Villotson example. So if this is not to contradict the theorem there, so the Villotson example must either be what, non-UCT or non-Z stable.
Oh, you're right. They're non-Z stable.
Okay. Right.
Yeah.
Cool.
Yeah. All right. Should have said that. Yeah. Exactly. They're non-Z stable, and they're pathological in many other ways as well. I mean, you could interpret this here as also being a strange thing for a simple C-star algebra to happen.
Yeah, right.
And of course, we don't know that they are not single generated. If you could also show that there would be another pathology happening, and it would also solve the generator problem for simple C-star algebras. I mean, at the moment, there are no examples known of a simple separable C-star algebra which is not singly generated. What this here maybe suggests is that maybe the Villotson examples are such an example, but I agree. I mean, I don't know. It will be very difficult to show either way, either to show that they're singly generated or not. That's my feeling.
Yeah. I mean, the examples from what I've heard are pretty hard to digest. Is that right? Or
yeah. So they are given as inductive limits of building blocks of the type that we saw. So I think matrix algebras over commutative ones. But what is happening is that the dimension of the spaces that grows very fast, or maybe is infinite dimension from the start, compared to the matrix sizes. And this means that what was happening maybe in each building block, you can compute the generator rank, and it's maybe infinite, or it goes to infinity, but that doesn't tell you that maybe there could be something happening in the inductive limit. Okay, so sorry, the generator rank is infinite in the inductive limit, but let's say finding a generator, you could maybe try to construct one in the inductive limit somehow with some method, but
yeah, right.
I don't see how to do it. I mean, some new ideas are needed, I would say.
Yep, thanks.
Are you able to at all relate this generator rank to stable rank?
Right. Yeah, this is quite curious, actually, that so the real rank relates, right? It's a lower bound. The stable rank seems to have no relation to the generator rank. Because take a Kunz algebra or any Kirchberg algebra, the stable rank is infinite, but the generator rank is 1. So it's not a lower bound, but it's also not an upper bound. I mean, it's actually, they seem quite, you can come up with examples where one is bigger than the other one that is happening. And I found it a little bit curious because some of the real rank is something like the stable rank, just with self-adjoint put everywhere. So you could think, I mean, I was defining the generator rank now also with self-adjoint generating tuples. And then maybe if you just look at generating tuples and you forget about self-adjoint, maybe that has something to do with the stable rank. But it doesn't. Because for generators, you can always pair two self-adjoints to one normal one and the other way around. So there's really no difference between the self-adjoint and non-self-adjoint version.
Because I was wondering if some of the other.
Sorry.
I was wondering if you knew something about the generator rank for like some of the other pathological examples, and I guess what I had in mind was like the cross products of Thiel and Kerr, because they have stable rank 1, so maybe they're less pathological than this guy, but I don't know. Or maybe just like some of the Andrew Tom's examples that are sort of much.
Right. that's a good question. So they, yeah, I know. I guess one has a better handle maybe because one has a more concrete description, but I haven't thought about it, and I also cannot immediately tell you either way if they are singly generated or not, what the generator rank is. I have no idea.
So, yeah, just another this generator rank. This is something you defined. Like, did people look at this anything like this before? Yeah, no. Okay, cool.
Yeah, no. I mean, people looked at the generator problem for sure. So I think actually, I mean, in the paper that I wrote, I elaborate on this, but this was initiated, I guess, at a workshop with Karen a long time ago. I think 2012 was it, maybe? Yeah, at AIM, and so yeah, this is when it started. So it's maybe 8 years old at most, you could say. But
that's very nice. Like when you compare it, like you did, to real rank and stable rank, it's a very natural thing to consider. But
yeah, it's true. Yeah. Yeah.
So no other questions. Okay. Yeah, Karen, did you want to introduce the next week or?
Just give me 1 second. Yeah. So next week we have Shirley Giffen. I think he's in the audience.
Is that next week? Isn't sorry? Isn't John speaking next?
That's in 2 weeks. Yeah.
Exactly. Yeah.
That 1 moment, please. That's the second time I've done that. Actually, is announced like at the talk a week ahead of time. There we go. 1st of December.
Okay.
Got carried away when Christmas happened. So yes, next week we have Jonathan Brown, who will be joining us from a different time zone. Nice enough to get up early for us. So hope to see some of you there next week.
Great.
Am I put now on the email list, I guess, to get the invitations for these future talks?
Yeah.
Cool. Thank you.
Awesome.
Okay.
Okay. Well, thanks everyone, and thanks especially to Hannes for awesome talk. And hope to see you again all next week. So.
Okay. Bye.
Yep.
All right, so we got to add Hannes to the email list. Should I end the meeting? All right. See you later, Tristan.
Okay.